Uh, okay, so we'll continue from last time. I'll just last time we proved Ito's formula. So to recall this statement, we won't go over the proof.
For
The
Brownian motions, I think, or
for Brownian motions, yes.
right.
So we
So one question I had was,
yes.
okay, I probably so it holds for any continuous functions, right? F belonging to C2.
Yes, yes.
Okay, so there is no need of this boundedness and so on.
No, and for so we first proved it for compactly supported functions, and then we approximated
Right.
bound, and we can do even more. So functions like mod x, which are not differentiable, so we can even use so for convex functions, even we can show a version of Ito's formula. In fact, that is used when we do local times and so, all those things. So the
Okay.
main technique is that we modify, like in PDE, we
Right. Right.
modify the function by a sequence of CC infinity functions, and then we we take the limit basically. So
Okay, but for most of the practical, or at least the questions that one sees in the first course of stochastic calculus, so
yeah,
for
then
F
we
in C2, F in
mostly
C2 should do it, right?
F, yes, F in C2.
So whenever you are asked to find some equality between certain two processes, so it usually has to do with finding the right F and then applying
Yes,
Ito's formula
yes,
on that. And
yes, yes.
okay, okay,
So basically, it gives you a technique to solve these stochastic differential equations. I mean,
right,
finding closed solutions. So
right,
mainly, uh, but when we want to show for functions like mod x, then we will get more deeper things like local time. So
hmm, hmm,
and so if you want to go deeper, then we have to go for more general functions. But for a
right,
first course, this is
okay.
the most useful
Okay.
version.
One more
So
thing that I've seen people
yes,
do is, okay, or at least maybe they don't want to do it, but integral of just BS DS, that is just Gaussian, and you can do all sort of, I mean, you can find all things just without bringing in all these Ito calculus, right?
yeah.
Because
So mainly polynomials, for most polynomials that will work basically. But
right, right,
if you want to go to like uh, um, the exponential martingales and those things,
okay,
uh, then if then we doing it for general f is better. So for
right,
example,
no, right, right. I mean, for example, if you had, let's say, integral 0 to t some f of Brownian motion ds,
yes,
so at least for nice enough things, you should be able to just get away without bringing in stochastic calculus.
yeah.
Uh,
So like that, we did this one, right? Um, we did bt squared, this one, bt squared minus t by 2, that thing,
uh,
the
right, no,
integral of
but it is still integral with respect to d, like this is integral bs dbs. I'm saying integral 0 to t bs just ds, let's say. I mean,
in the, so bs ds would just give uh, a random area under the graph, right?
right. So yeah, I mean, you can get all sort of things, yeah, like its distribution, mean, and everything.
Yeah, that is just we can exchange by Fubini uh, integral with respect to ds and the expectation. That will give you the mean and
Yeah,
variance.
I
Yeah.
mean that it is that this distribution is itself Gaussian. That is also clear, right? Because just you
Yes,
could take
yes.
Riemann sums and all things.
Riemann sums, limit of Riemann sums,
Yeah,
so it
limit
will
of
be
Riemann
Gaussian.
sum. Right. Okay. So, but only when you have these integral terms with respect to dws, you have
Then we
to
have to, yes.
it's better to okay.
So uh, mainly recall that f of bt minus f of b0 equals to integral of 0 to t f dash of bs dbs plus half of f double dash of bs ds. So this was the form we proved. Last time I introduced the Ito processes, which are processes of this kind. So which are represented by these equations. So xt equals to x naught plus integral of 0 to t sigma of s omega dbs plus 0 to t b omega s ds. So this term,
Right.
this corresponds to the martingale portion, and this corresponds to a drifting thing. But the main point is that if we choose b to be nice enough, then this term will give you um, uh, it will give you a finite variation process. Where, so what I mean by that is, it omega by omega, it will be a difference of two monotone functions. Or you can say that if you define a measure small mu of t, small mu of 0 to t, the interval 0 to t given by this integral of 0 to uh, integral of 0 to t omega s ds, then that will be a uh, that will be a read-on measure. That will be a read-on measure. So that is what I mean by a finite variation process. So uh, the thing is that
Yeah.
most of the times we like to work with Brownian, which includes the martingale part, some drift. So this drift can be,
But yeah, I have seen that. I mean, this is this stochastic differential equation form that you have written it, right? Like it is.
yes,
So basically, you are saying xt satisfies the differential equation, or in other words, xt equals integral of
yes.
sigma of s comma omega dbs. Right. What was this omega? I seem to have forgotten.
Omega is the I mean probability space, the random.
Uh, okay.
Omega is the, like, we are in a fixed probability space, omega
Okay. Okay.
fp. So
But most of the times, I mean, I'm just, this is all informal and I'm just asking you.
yeah,
So most of the times I have seen this omega not being there. So, I mean, usually I've seen this
I have
equal.
just given it explicit.
I see. I see.
Yes,
So informally, this means that just that
yes.
xt
This
behaves
omega by omega. I mean omega by
right,
omega.
right.
This is true.
Uh, okay. And how, okay, and the second integral is made sense bringing in all these step processes and so on, right?
This one,
Yeah, with respect to dbs,
dbs. Yes.
yeah, I mean, this is supposed to be uh, like omega by omega. This should give you some path or something, right?
Omega by omega, this will give you a martingale. Yes, continuous martingale. So
Uh,
integral. So recall that a stochastic integral is a martingale.
right.
So this
So
is
yeah.
this is
s-
yeah,
So so basically, you are writing xt. If I just ignore the omega, this is just xt equals x0 x naught plus integral 0 to t sigma of s dbs.
yes,
Uh, so both, I mean, the left hand side is stochastic process, which
yes,
is right. Uh, okay. And this b is usually written as mu, right? This is the drift part.
yeah, 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 yeah. This
Okay.
really the so for example you can write, so you can if you take a simple example, like if I say xt equals to bt plus this t squared, or let's say okay, t squared, then this is a close enough process to a Brownian motion, right? It's
Right. Right.
so these things are in like random graphs and all those things. So we get uh, limits of the walks and so forth, like these,
Right.
right?
Right.
So I can represent it by just saying that this is equals to integral of 0 to t 1 times dbs plus integral of 0 to t, um, this is s 2s ds.
Right. So this
So
becomes so dxt equals um, dbt.
dx equals to dbt plus 2t dt.
Right. 2t dt. Right.
So most processes can be expressed in this form. I mean, uh, we don't only want functions of Brownian motions. We want Brownian motion plus some things also. So
Okay.
a martingale portion like this sigma dbt.
Right.
Sigma represents the standard deviation. I mean, and
Okay. Okay.
and BTDB, the BTDT should represent the drift. So this is
Right.
the uh, additional drift, which is making things like
Uh,
expectation of it is non-zero and all those
right.
things.
Right. So now, so if I write f of tx, if I take some function f of tx and write uh, some function of xt and t now, like let's say
Yeah,
yt is uh, t comma xt, f of t comma xt is yt. Then again, Ito's process will give you some other thing. So yeah, I just want to know whether we are yet to prove that, right?
yeah.
That dyt, or rather
So
df equals
df. So here we need to apply the Ito's formula for two variables. So here we only did for x, right? F of x, where we replaced
uh,
x by the Brownian motion.
can you go above I mean the one that we had done earlier.
Yeah, yeah. So it is, yeah, this one. So if you
Right.
recall, we replaced x by bt, and then
Yes.
apply Taylor's theorem to derive the heuristics,
Okay.
right? So
Right.
when we do f of t comma x, we'll have to use the two variable Taylor's theorem to get a get a like to get the idea where what the right hand side should be, right?
I see. So the earlier, the okay, so the Ito's formula that we have proved earlier would allow us only to write this
F of
apply.
x,
Yeah, yeah, I see. Only
f of
one
b.
variable. I see.
Yes, but if you want to do f of t comma bt,
Okay.
like if you want to find d of gt times b times h of
B
bt.
BT.
So
Right, right, right. So the second the in the product the second term is the
this is
x.
this is we know
This
this one
yeah, yeah. The first one is the t
first
variable. Second one is supposed to be the x variable or
x
something.
variable. So we need a two variable version of this to apply.
I see.
uh,
Is there any point in going to three variables and so on? So, or but you would rather look at three variables as just you just take other two space variables t, let's say t and u as one variable and
I mean,
then apply.
I mean, there is so you can state it in for Rn, and the form that it comes in, it is not
Okay,
too very complicated. I mean,
I see.
so you'll just have partial derivatives instead of the regular. Uh,
Okay, okay. So okay,
so
so we are going to see the Ito's formula for two variables, right? Like
two
for any
variables.
f of t common. Okay, okay, great, thanks.
Yeah. So I'll just do the heuristic
Yeah,
derivation.
yeah, yeah,
So
yeah, yeah, sure, sure.
without any proof. So for like we did while doing the heuristics for it was formula for one variable. So if you take a function, so f is a function of two variables, so f of t comma x, and what we want to do is find uh, we want to replace t with t and x with xt instead of just bt, because that is more general, right? So xt is like this. We would like to see a form for f of t comma xt. So how should we go about deriving it? So like last time, we have to find the Taylor's expansion of f. So if we just write this out, then we get df dt, there del f del t times dt, plus we get half d2f dt dt2 dt squared. And recall that we want to ignore terms of the form dt squared. We want to keep only terms of the form dt, because when we are dividing by dt, then these are the order 1 terms. This should go to 0. So and so on. And for x variable, we will have del f del x dx plus 1 by 2 d2f dx to dx squared plus dot dot dot. So we want to ignore terms of this form, but we want to keep terms of dx squared, because dx squared will contribute to a term like dbt squared. And we saw that dbt squared, if you remember the um, heuristic, is that dbt squared behaves expectedly like dt. This is the most fundamental heuristic that fundamental idea that we should always remember, that a Brownian motion in time t moves a distance root t. So uh, we want to keep terms of that form. So okay, let me just write this now. So if we simplify this a little, we get df del t dt plus del f del x mu. So it was bt, right? I took bt. So bt dt plus sigma t. Uh, okay, so I'm. Uh, where did it go? So we want to replace dx by dx naught or dxt. So recall the form of dxt. Dxt is sigma t dbt plus bt dt. So we want to replace dx by dxt. So if we do that, then we get terms like this. This is the this one for del f del x dx, plus we should have an additional t2f dx2. And now if we so if we now squared this term dx squared, so what are the terms that we will get? We will get bt squared dt squared plus sigma t squared dbt squared plus a mixed term like dt dbt. So recall that if dbt is like root dt, then dt dbt is like sorry, it is like dt to the power 3 by 2. And when divided by dt, if we divide this by dt, then the remaining is we have a root dt term remaining, and that will go to 0 as t goes to 0. So that is the main point. So here the here the only term that should survive is this sigma t squared dbt squared, and we want to replace dbt squared with dt. So we should get del f del t dt plus del f del x b, bt dt plus sigma t dbt plus half sigma t squared del f del x d2f dx2 dt. So if I now write this in a compressed form, we should get df equals to del f dt del t plus uh, bt del f del x plus sigma t squared by 2 d2f dx2 plus sigma t del f del x dbt. So this is the form of df that Ganeshwar was asking. So here, like this df dx, if we have a function of this form, then we can write df in this manner. Uh, so uh, so in general, in even more general form, there is a you can prove Ito's formula for Rn, and should I state it? I mean, uh,
For Rn, I think maybe you can just leave it for the
yeah.
next.
So I mean, we don't gain too much. I mean, so instead of this sigma t, now you will have a matrix like a covariance matrix, which will be given, and then you have to so instead of the sigma being a um, instead of this sigma being a single value, you will get a matrix of sigmas. That's the
Yeah.
entire point.
So the derivative will become this Rn to R derivative. So you get a linear transformation and all this
Yeah, yeah,
matrix.
sort of like that. Yeah, and you
Right.
can even take just term by term derivatives, and you will get a
Uh,
thing like trace of uh, basically this
yeah. You get this
the
trace of
thing will have to be replaced by a inner product. I mean, the Frobenius product that we know for
hmm, hmm,
matrices. Yeah,
hmm,
like that.
right.
It is unnecessarily complicated. I mean, it's better to state. So next time I will state the form for semi-martingales. That is much more useful than these forms, because there the entire thing is predictable and you get a very compact expression, and that is the form that you will that is the form that most general form you can say that is of use to us. I mean, we will never need a form which is much more general unless we are like researching in stochastic
No,
analysis.
I mean, you mean this is the one that is more useful to us, or the next time that you will do that one?
The next time, so I if I so if you recall, these semi martingales are like xt equals to mt plus at. So this is so as an Ito process is a special case of a semi-martingale, right? I
Okay,
mean,
right,
in
right.
this case, the martingale is expressible as a stochastic integral with respect to Brownian motion, and this at is this integral with respect to the
Yes,
drift term, right?
yeah.
Uh, yeah. So, but instead of having such arguments for, I mean, instead of having Brownian motion as the integrand, stochastic integrand, and um, the increasing the process, the finite variation process being a deterministic one or even a random one, we can replace it by general martingales and increasing processes, right? Finite
So
variation.
yeah, you mean instead of just with respect to Brownian motion, you take more general
Yeah,
martingale, right?
more general. And the point of this is, since we have already seen what the terms come for Brownian motion, the entire the formula that will arise for xt, so Ito's formula for f of xt, this will be very much predictable. I mean, you will instantly know what the terms are because of the similarity with Brownian motion.
No, but do we? I mean, I'm just asking. Is it of
Yeah.
uh, are processes or integrals without or integrals, stochastic integrals, something more general than Brownian motion, more ubiquitous, or I mean, do they show up more, or
So, for example, if you want to integrate, so instead of the integrand being uh, so for example, you can take
uh,
martingales which are more complicated, you can say that
okay, I'm just like guessing all this Poisson point, sorry, Poisson process, jump
yeah,
processes,
yeah,
and so
in that
on. You
case you will get a the increasing process will be the so instead of a normal the usual
right,
point process, so
right.
suppose the point process is taking place in a random area. Okay,
Hmm,
so
hmm,
say underneath a curve, for
hmm.
example. So in that case the form will be more complicated than that of a Brownian motion, right? So
Right.
you, for example, instead of the Brownian motion, you can have a Brownian bridge as the limit. So the most useful ones are the functionals of the Brownian motions, like we saw, like dt plus t squared and
Hmm,
all those
hmm,
things. I mean,
right.
even they are. I mean, Ito processes are general, are very general enough. So, but we can go even further uh, for stating it for semi-martingales, because uh, it is maybe worthwhile to see what we are missing out when we are looking only at Brownian motion. So there
Okay.
are so for example, there are for some nice formulas like the Kunita Watanabe's inequality, and
Right.
the and another point is that if you there the expression for semi martingales is not at all very complicated, and it's very similar to the form that we did. So
Uh,
that's
so,
why.
so I'm guessing in when you write this Ito's formula for Brownian motion, and if you compare it with the more general semi-martingale, so all these half and everything, this constant come up
Yeah, the
because
exactly
of
same.
this.
They will be exactly same. Just instead of dt, the since the since the quadratic variation of Brownian motion is dt, you will get the quadratic variation term will only change. But
Okay.
that is just a matter of notation. I mean, in, except for that one term, everything will be like
Uh,
ditto.
I mean, which term would change here in
So
this
here,
expression? So
so
the drift term is bt, so that would stay the same, right? I mean,
drift term is, yeah, that will stay the same. The term that will change is dt. So here we had a dt, missed that. So
right.
dt instead of dt, so maybe I can show you instead of explaining, I can just show you the book, uh, because it's so very useful that it, and it is, so this is the book by Legol. So here, It's visible, right?
Right, yeah.
So you see, you can replace it by p many semi-martingales here in the
Okay.
argument, and this is the term f of x0. So recall the it was formula for martingales. I mean the Brownian motion. We get f of bt equals to f of b0 plus the df uh, f dash of bt dt f dash of bt dbt plus half of f double dash of t bt ds.
Okay. Since there is only one variable, it becomes dou square, dou x square
Yeah,
like this.
instead of so here if you replace xt by just bt, then this term, this is the quadratic variation. This
Okay.
will just be d of the quadratic variation of Brownian motion evaluated at s, which is just
Uh,
ds,
right.
right? So for
I
for
see. So when it was Brownian motion, it was just t here. So that's how you get this dt.
yeah, instead of dt you just replace it by the quadratic variation of the um, semi martingale.
Okay. So I mean, if instead of this p many, if there was just one, it would just be quadratic variation of dxi, right?
Yeah, yeah, quadratic
Okay.
variation of dx1, just that.
I see.
And similarly for mixed terms you don't really get too much difference, right? So if from this one itself you can derive the form for Brownian motion for uh, p many Brownian motions, for example.
Hmm. Yeah.
And even in this case, if you replace
Okay, so what happens if all are Brownian motions and the in this quadratic variation for xi xj? So if there were in the cross terms,
yeah,
you
so
still get s.
so there you have to know the joint law
I
of
see. I see.
how they are related. If you take independent ones, then these cross terms will all vanish basically, because
Okay. Okay.
in expectation they are zero, right? I
Hmm.
mean,
No, I mean when I and j not equal to, they will vanish. But
when I
uh,
equals to j, then you will get just dt
yeah, yeah, right, right.
ds.
So for independent, this is just like the sum of p many
P many, yeah,
Brownian motion. Right.
yeah. So this form is very compact, right? And this is the form that we saw for Brownian for f of bt. Exactly
Right.
same.
Yeah, yeah,
So
yeah.
it's what knowing this, even though it is for semi martingales.
Uh, okay, so okay, but there is no derivative with respect to t. Like this is just a function of. So there is that also, right?
No, so since they are semi martingales, you
I see. You can take. You could
can
treat. You could add
the
one more
Brownian
variable
the
t.
martingale part as zero, and you can
Uh,
just have an increasing process, which is just t, which is
no,
deterministic.
I mean the earlier one that we did. So f of Brownian motion, f of let's say x1 comma t. So
Yeah. So
you would treat this the second semi martingale as a just an
uh,
increasing process.
yes. So this
Uh,
t itself, that is a semi martingale,
yes,
because
yes,
it can
right,
be written as zero plus t.
right.
So this gives you
Okay.
everything basically.
Okay. This is more.
This
I
is
see.
even more powerful.
And I see. So that's how you get. So when you take all these terms in dt, so you had this partial difference with respect to t. So that's okay. So
Yeah.
you basically
So
had
you
three
will get,
terms. You had
so
three terms
instead
with
of
respect to dt.
dx2, instead of del x2, you will get dt. If you replace by xt and t instead of
Uh,
del x2 here,
right. No, I mean with respect to dt, you had three terms, right? So you had del
yeah,
f by del t,
yeah, del f by
uh,
del t. Then we had
del f by del x mu t.
yes, del f by del x mu t and sigma squared t by 2 del f del x to dt.
Right.
So
So
for the for this, so if you, so if x1 x2, this is equal to like xt and t, then or then the term tt, this will be just dt.
okay, and txt would be
And txt would
and even I think like xt would also be dt, right? That will also give you
yeah, if xt is a Brownian motion, you will get dt.
dt. And what about t and xt?
uh, so here you will get sigma t squared. Where is the bt term? Yeah, so this one, so uh, this is the finite variation process.
Okay,
So you will have to compute this term. So btj, um, btj minus btj minus 1 into tj minus tj minus 1, the summation j equals to 1 to n, and then you have to take the limit
ah,
value.
okay, 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 so you'll have to do this is probably something just like Brownian uh, uh, right. So probably this should you should get dbt somewhere. So I'm guessing this is where you get that.
Yeah, the dbt you will just get from the
First,
dx1.
I see.
So here, where was it? So
In
here,
the second
dx1.
term, right? You will get dt there. Uh, but then it would also be I see dou f by dou x dbt.
Yes.
Uh, so okay, whatever that extra term is, I mean, since we know the Ito's formula for Brownian motion in T, so probably we can work out what this quadratic variation and the cross product between T and XT is.
Yeah, yeah. So
Correct.
the thing is that,
Shouldn't there just that be? I mean, it looks like Riemann sum
yeah,
what you wrote, right? So that
this one.
yes,
Yeah,
um,
this is the uh,
I see. Probably you get some DT term there.
oh, sorry,
So
sorry, 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 sorry. I miswrote. I miswrote. So if you, so this, if xt1, if xt1 and xt2 are two semi-martingales, and you get mt1 and mt2 as the martingale parts of xt1 and xt2, then this bracket xt1 xt2,
it's
that
just the
will
martingale.
be only involving the martingale
I
part.
see. And this since this martingale has zero, so that would probably be
You
zero.
get zero. You get
I
zero.
see.
Yeah, I missed.
Yeah,
I
no issue.
thought it was b. Yeah, then there
Right.
you would just get zero.
Okay. Okay.
So that form is even more useful, right?
Yeah, yeah, this is much more neat. Yeah. And this is.
And very compact, and it's just a matter of working these terms out. There's nothing
Yeah, I
else.
mean, now that you said the cross terms would cancel out, so that probably makes things easier.
Yeah, it will be very easier. So uh, another another form. Um, for example, if you have if you have two processes who share this same martingale part, then if the cross terms part, the cross terms, that will give you that will only give you the quadratic variation of the martingale. So that will be even more easier. to handle.
Sorry, can you repeat the last sentence?
So for example, if you have two processes which have the same martingale part,
Okay.
then the cross terms will only give you the quadratic variation of the martingale,
So they only differ in the increasing process, you
increasing
mean?
process. Yeah.
Okay.
So the only problematic, the quadratic variation, the cross term will only be the uh, quadratic variation of the martingales themselves, right?
Right.
It won't it won't matter too much. So
Uh,
the term that will arise, they will be very similar.
right. But okay, what I mean, we haven't seen any. I mean, or at least in the standard, all these exercises, uh, uh, two semi-martingales with the same martingale
Yeah.
part,
So
and
as an example, um, if you take this, if xt is this, xt1 is this, and xt2 is bt, for example,
okay,
then xt1 is
okay,
basically a hidden
you
Brownian motion.
you probably uh, okay. You mean to say both have the same martingale part?
Yeah, because it's implicitly hidden that this is actually a Brownian motion.
Okay.
It can be
Uh,
shown. So
so basically, you again apply. Probably you can apply still apply Ito's formula to the x1t and write it as bt.
to x1t and write it as,
I
yeah.
mean, somehow show that x1t equals bt. If you manage to do that, then you're probably done, right?
No, you won't be able to show that dxt1 is dbt. You won't be able to do that.
Uh, no,
What
but
you
this
have to do is
right?
say that this has continuous paths,
No, this sign is just mod of this thing, right?
mod of
Uh,
this thing. And so the main thing is that you need to compute the variance and check that it is t.
okay.
So that will give you that the increasing process of sorry, not the increasing process, the quadratic variation of this is given by dt.
Okay, but wait. So you're saying I mean, using the both two variable Ito formula, we won't be able to show that x1t is just bt.
No,
Uh,
you have to show that it's a Brownian motion, but you cannot show that it is this bt itself.
right. Probably I can show. I see, but you can show that it is some Brownian motion.
Yeah. So
Just x1.
for example, bt and minus bt are both Brownian motions, right? But they are not equal.
Yes. Yes.
So you have to show that it is in a distribution, it is a Brownian motion.
Yeah. That's what I meant. I mean, using just the first two variable Brownian motion Ito formula, you should be able to show that x1t is has. I mean, at least in up to distribution, this is just like bt.
Yeah. So and so even easier way to do that is uh, so if you have to show that in distribution it is bt, what you have to show is that the quadratic variation is given by t, right?
Sorry. Yeah, there's some disturbance on my end. Yeah.
Yeah, yeah. So
What? Uh,
quadratic
uh,
variation should be given by t. That's all you have to
right.
show.
No, but shouldn't you also show that it is actually Gaussian? This x1t.
that will follow. If you manage to show that the quadratic variation is t, then
right?
you, then actually I am actually using a stronger theorem that Brownian motion is the only
You would
martingale.
need some right, but then you will have to again show that x1t is a martingale
It
uh,
is a martingale that is easy. It is a stochastic integral.
of no. I'm worried about the sine function. So
Sine is bounded in L infinity, and so it is L2
right.
of lambda t
Okay,
comma p.
okay, okay, okay. So x1t is a martingale. Okay, and then you are
Yeah.
using okay. So that way you get up to distribution, but showing that it is actually equal to bt is I see.
So in that case, what you have to do is compute the covariance of uh, so 0 to t1 and 0 to t2, and you have to work out that the covariance will be given by t1 mean t2 basically,
Uh, to show Gaussianity or
to show that the covariance matrix match for
uh,
ti mean tj, that I mean that
yeah,
are.
but how would you show that x1t equals x2t? Would that, I mean, this covariance matrix will show you that x1t equals x2t?
No, no, it
Yeah,
won't show you that x1t equals x2t, but it will give you that the quadratic variations.
yeah. I mean, I agree that probably somehow you can show that x1t is Gaussian and uh, you can show, you can find out its covariance and everything.
Yeah, so what I am saying is you can show that xt1, xt2, this is just given by dt, because they will have the same martingale part.
But
And
yeah, how do you prove that they both have the same
yeah,
martingale
so
part?
you can just compute that Riemann, that sum. So uh, so so it will be this
I see.
uh,
Because this is just a step process. I mean, this is not even
step
step. This is a
process. Yeah,
constant. This is basically constant
constant.
process.
Yeah,
Yeah,
yeah, yeah.
I see. Uh,
And if you,
okay.
so given a partition, you will further
Right.
subdivide it so that it stays positive. So
Right. Right.
SGN is
Right.
just one.
Yeah. You can always given any other time interval, one to the left and one to the right of origin. You again
Yeah.
can find out that. I see.
Yeah. So
Right. Because the sine is a step. I mean, it's even much better than a step function. You can actually work out.
yeah, you can actually work this out. So what my point was is that you might get sometimes uh, processes which have, whose cross terms are given by the same sort
Just
of
dt. Yeah.
just dt. So
Mhm.
that's what I'm trying. So even though the processes are different, the martingale, the cross terms of the martingales turns out to be nice. So
Right.
here you,
I mean, here, okay, maybe if you add the increasing process is zero in both of them, but if you add some two different functions to
yeah.
something like that, yeah,
So this one actually comes up when you define local times basically.
right. But
So
just showing, I mean, showing that they both have the same martingale part itself is slightly tricky, no?
uh, they will not be equal, certainly they will not be equal, but the cross terms, they will be very nice. I mean, if you want to compute the uh,
No,
cross,
I mean, even no, you mean to say they have the same martingale part and uh, so
I mean the
basically,
martingale part have the same distribution, that's what I meant actually. So uh,
uh,
and the
so
cross term,
basically, your x2t should be could be some another independent zt. Is that what you mean? No, right?
no, I mean here bt and this are interrelated, right?
Right. So basically x1t equals x2t, right? Here.
Not equal. I mean, uh, not equal almost surely, but equal in distribution. I mean,
So
they won't be equal, right? So, uh, I mean, for example, um, so I mean, even if you just take an even simpler one, so if you take
so I
xt1
mean,
equals to minus bt and xt2 equals to bt, uh, then even though the martingale parts are not equal, they will have a nice cross quadratic variation.
will that be positive? This.
That has to be positive. Quadratic variation has to be positive.
Uh, okay. Uh, no, I mean when you took this quadratic term of x1t and x2t, what was that?
X1t and x2t, that was just dt. I mean, in limit. I mean,
Right. So basically, you just need something of the same distribution, right? I mean, for example, you could have an x3t, which was some, let's say, what's a nice thing? Uh, Probably bt by 2 plus zt by square root, like bt by
yeah,
square root 2
yeah,
plus zt by square root 2. So then,
yeah,
even then, the cross term would still give you dt, right?
yes, and the cross terms will interact nicely.
Yeah, yeah, yeah. Okay.
So even so, the point is that if you know this form, then
Okay. So you
for
mean to say,
processes which interact nicely, you can have a nice expression for this.
okay. So for the special case of Brownian motions, so even if they don't have to be independent, but if they have the same distribution, the cross terms would be just dt. Is that
Cross terms will be dt in nice cases. So, for example, in like in the one you took, if you take so x suppose xt2 is bt and xt1 is some bt by root 2 plus zt by root 2.
right?
Is that a Brownian motion? I mean, variance is half. Yeah,
Yeah. So
this is
that is
this
the
is a
Brownian
Brownian
motion.
motion, right?
Yes. Yes.
And say z is independent of b.
Right.
So even in this case, the since this is the martingale part, this is the martingale part, you will have a nice interaction between the uh, I mean this
Okay.
term
Okay. So
cross
bt
term
and bt cross term would interact nicely. Zt bt would interact
would
different.
just be zero.
I see.
So that's what I meant actually.
Okay. 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 Right. I mean, I'm not. Uh, when you say both have the same martingale part, I probably have not very clear on that. But yeah, we can take it up from next time. So I think
Yeah,
uh,
I mean, if they have the same martingale part, then it is even easier, right?
right,
So
right.
you might have terms like that. So xt1 can be bt plus some drift, and xt2 can be bt plus some another drift.
Yeah,
So
yeah. That special case is clear to me. I
that
mean, it is
and
basically the same part with up to increasing process being different.
yeah, and
Right.
even if they have the same distributions, you can have so in special cases
So
like this.
for example, when you said minus bt and bt, when you say they both have the same martingale part,
They have the same martingale part in distribution. I mean,
right?
bt and minus bt.
Okay.
But so if you want to compute the quadratic variation, the cross
Right. I mean, in
quadratic
that, by that terminology, like two independent distribution would also have the same distribution, right?
yeah.
And yeah, BT, for example, here BT by BT and ZT, they both also have the same martingale part. Would you say something like that? I mean, I
No, no.
like what is
I must have. When I say same martingale part, I mean similar. I should have said similar martingale parts. That would have been better word. So what I mean is that if you have ZT and BT, the
okay?
interaction, I mean, as long as they have the same distribution, you most likely will have uh, nicely behaved cross terms. So I mean, you can directly compute them in some
Okay.
sense.
I see. Okay. So you mean those processes where you can actually the quadratic variation or of the cross terms come out nicely in some sense,
Yeah,
something like that.
yeah. And even if they are like hidden terms like this, so
Yeah, yeah, yeah.
this is like hidden as a Brownian motion. Even then, it will behave cross. The cross terms will behave nicely.
Ah, okay, okay, okay.
So that's what I actually that's what I
Right.
meant. So
Yeah,
either they are
right.
fully independent, in which you directly get zero, or you
Hmm.
can get something even nicer,
Yeah, yeah.
or
So for
something
in
nice.
yeah in this xt1, so which is this bt by root 2 plus zt by root 2, you I mean you get a slightly nicer term. So one thing gives you zero, and one thing gives you some positive things. T by root
Yeah,
1.
yeah, yeah,
Yeah, yeah. So yeah. Okay. In that case, I have posted the problem sheet that Argyadeep sent me on this thing. Uh, so probably I'll do some problems in the next time then. Uh, yeah, so we are
yeah,
done.
yeah,
We are more or less done with this ito thing. So we'll just try to apply them and
yeah,
see, like, get uh, used to how to apply that and
yeah, yeah. So
also
I
something.
think it's better if we let the next 1 or 2 classes be about like easy applications.
Yeah, 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 just exercises and applications and
Yeah.
what probably
Once we
yeah.
get familiar with that, then after
Probably
that
we
we
can.
can
Yeah,
make
yeah.
this
I would
like
I would suggest let's move forward only after we are all like very
yeah
much comfortable with.
comfortable
So
with
I
the
mean, this is an
tools.
informal thing. It's students' informal thing. So unless
Yeah,
we all are okay with things, we can probably yeah.
yeah,
Okay. Yeah. Thanks a lot, Argadeep. I mean, I had trouble understanding this E2 lemma formula, all this. I mean, the proof part. I mean, anyway, I don't remember most of the proofs, but at least
yeah.
what the thing is saying about and what is the formula about that I
Yeah,
had.
I mean the main thing is about remembering Taylor's theorem. As long
Right,
as we
right, right.
remember that, we can derive it on spot,
Yeah,
even
yeah,
if we
right.
forget it.
Yeah, right. Yeah, thank you very much.
Yes,
We'll
thank you.
take it. Yeah. Good night.